In this video, we're going to look at a really important concept, which is a line integral of a vector field which includes a dot product, f dot dr, where both f and dr are vectors. Before explaining this, I'd like to raise the analogy with surface integrals, and for that I have these slides here. So you will remember that when you were doing surface integrals last chapter, you started by calculating a surface integral of some function with ds, and ds was the scalar differential of surface, and this was the equation for it. Yeah? But then I introduced to you the calculation of the flux, and this was very similar to fds, with the difference that both f and ds are vectors here, and we are doing the dot product. Okay, and remember that ds now had the length of this vector ds is the same as the scalar ds, but the direction is normal to the surface, right? So that in fact the ds vector could be calculated as n du dv, similarly to the ds scalar, but without calculating the norm of the vector n. Okay, and you also had to remember to do the dot product. Now in 4.3 we are studying line integrals of f dl, and the dl, the equation for the scalar dl, is the norm of this tangent vector times du. So notice how similar this is to this. Yeah. So now of course we are going to complete this table by adding something here. And what is this something going to be? It's relatively simple to understand. It's going to be an integral of a vector function f dot a vector displacement, differential displacement dr. So f dot dr, and this is a vector and this is a vector. Okay, and this dr is going to have the same magnitude as dl, but it's going to be in the direction tangent to the curve. So that's going to be the direction t hat. Okay, so that dr vector is t hat times dl. But luckily, you know that this vector dr over du, before we calculate the norm, this vector is tangent to the curve, right? Because this is the tangent vector. And therefore, the equation to calculate dr is simply to calculate that tangent vector and multiply it by du. It almost, when I write down this equation, it almost seems like a very silly equation, right? It's dr equals dr divided by du multiplied by du, so the du's cancel out. Exactly. So this is literally the differential of the position vector, dr. Okay? So we are going to calculate these types of integrals, f dot dr, and you will have to remember to do the dot product. So it's the same warning that I was giving when you were calculating the flux. Okay? So let's write this formally in the whiteboard. We want to learn how to calculate integrals that look like this. It's a curvilinear integral or line integral of f vector dot dr vector. Okay? And remember that this is a dot product. Now, maybe I can center this here. Another way of writing this is if you substitute the fact that dr, so let me draw what dr is down here. So if we have a curve like this is our curve, see? Okay, and this curve is a parametric curve. So we have r of u, which points from the origin, let's say that the origin is here, to the curve. Yeah, so this is r of u. And now we increase the parameter by an amount du. So therefore we move along the curve to a certain place here, right? So this will be r of u plus du. And this will mean that we have moved along the curve. We have moved along the curve by this vector. And this vector, we can call it dr vector. Okay, so that's the meaning of dr vector. If you recall the definition of the differential of a vector, this should be familiar, right? Also, if you recall the definition of the derivative of dr, so if you recall that dr over du is defined as the limit when du goes to 0 of, let me write it there, of r of u plus du minus r of u divided by du. Yeah, that's the definition of an integral. So of course, if you multiply this by du, you are multiplying this by du, so you are canceling this out. So you end up with this differential vector, which is the difference or the vector that points from r of u to r of u plus du, because this is a subtraction of two vectors. So it's this green vector here. Okay, so this is exactly dr. So dr is defined as dr over du multiplied by du. Okay. Alternatively, you can see dr as dl that we were finding earlier, but in the direction tangent to the curve. So let's call that direction t hat. This is a unit vector pointing in the direction tangent to the curve. So dr has the same length as dl, because remember that dl was defined as the norm of this vector times du. So clearly the length of dr is the norm of dr will be equal to dl, yeah? But the direction is tangent to the curve, okay? So this would be two equivalent definitions of the differential dr vector. So if we substitute this up here, you can write this as the line integral of f dot t hat dl. Okay, so I basically substituted dr vector with dl t hat, and then I just group the vector t hat, I put it inside of this bracket, so I do the dot product with f. And notice that this becomes just a scalar function, f. So this becomes a normal integral f dl. Okay? So that is this important definition of this line integral with a dot product. In the next video, I'm going to give why this is useful and some intuition as to what it means to calculate this integral. Okay? So see you in the next video.